All right, moving forward with exponents, we have several rules on how we work with things with exponents. I mean things like how do we add terms with exponents, how do we multiply terms with exponents, etc. So the next 4 learning targets are working with operations with exponents. So this first little exercise is kind of to show you how things can look very similar. Like all of these problems have a 2, a 3, and an x and an exponent of 2 for the most part. But they all are going to have very different solutions. So as we move forward, you can't just look at a problem and glance at the numbers and think you know what to do. You have to look at every little piece of the problem and notice whether you're adding, multiplying, whether the terms are the like terms, unlike terms, etc. So let's take a look at example 1. The first thing I notice is that I'm adding these 2 terms together. So when I'm adding terms, that's when like and unlike terms come into play. So the first thing I'm going to notice about this particular problem is that these are like terms because both things have an x squared in them. So I'm going to write above here, I'm going to say these are like terms. And the way we read this type of problem is this says 2x squareds. So that's saying I've got an x squared plus an x squared, right? I've got 2 of them. Like if I had 2 oranges, I've got 2x squareds. And then I'm saying that this is like 3x squareds. So there's an x squared, there's an x squared, and there's another x squared. So now I can say, okay, well, how many x squareds do I have? I've got 1, 2, 3, 4, 5. So because I'm adding, I'm going to add those all up. So I've got 5x squared, which, if you guys remember from earlier lessons, that makes sense because when you add like terms, you just add the 2 and the 3 together to get 5. Okay, so that's the first type of problem we've done before, adding like terms and combining those like terms. Okay, so that's our first type of problem. All right, now the second type of problem, I'm going to move down to here to this one, is where we have unlike terms. So this is a problem where I've got 2x squared and 3x. Now x squared and x aren't like terms. I'm adding, and what have we talked about with unlike terms? Can we combine, can add unlike terms? No, we can't do anything to this problem. We have to leave it like this. This is the best we can do. You cannot add unlike terms. So I have to leave it like this. That's the best simplification I can do. Versus the top problem where I could actually combine them and get a nice one-term thing. Okay, so that's adding terms with exponents. So what about multiplying terms with exponents? Okay, this has a very different type of pattern here. Okay, so when we look at these 2 problems, notice that now we've got a multiplication symbol. Multiplying is very different than adding. Okay, multiplying, we're going to have to expand this when we multiply, because when we talked about in the last lesson, if I've got 2x squared, that's the same thing as 2 times x times x. Now I can do this because, see how I'm using times symbols? I didn't do that here in this other problem because I'm adding. So I didn't expand them. But because here I'm multiplying, I can just take that times symbol and tack it down right here and expand this 3x squared. And now I've got this nice long expansion. And in the last lesson we talked about how to expand things like this and how to simplify it. Well, I've got 2 times 3, which is 6. And I've got 4 x's. So this is one of those cases where I started off with x squareds and I ended up with x to the 4th. Versus the first one, I have x squareds and I ended with an x squared. So adding and multiplying these 2 things are very, very different. Okay, and today we're going to talk about patterns we can use to make this easier. Okay, let's take a look at the last one. The last one, it's important to notice that, let me use a different color here, that we have unlike terms here, right? Up here, these were like terms, and we multiplied them. Okay, and we talked about how adding, you can't add unlike terms. Well, can we multiply unlike terms? With multiplication, yes, we can multiply these. I'm going to expand this just like the top one. There's 2x squared, and then here is 3x. So see how all of them can be multiplied? This becomes 2 times 3, which is 6, and then x to the 3rd power. So at the end of the day, something very interesting about multiplying things with exponents is that a general statement here is that multiplication is much more flexible. There's more math I can do with multiplication than addition. Addition, on the other hand, is restrictive. I can only add things that are like terms. I can't add things that are unlike. The math doesn't work, but I can multiply terms and unlike terms as often and as many as I want to. So this is something I want you guys to really pay attention to. Look at your problems, look what operation you're using, look at what kind of terms you're working with, and then make a logical decision. Okay, it's not always obvious, and as we get into second semester, you guys will have to make some of these choices, right? You're going to have to really look at these problems and decide, well, what makes the most sense going forward, okay? So there's a nice pattern, though, with multiplying, right? I don't see how I had to expand each of these every time. Let's see if we can find a pattern with this expansion, okay? So we're going to try and expand all these problems and see if we can find a pattern. Okay, math is about patterns, and we like to make things easier for ourselves. So the first problem is x squared times x to the third. So there's my x squared, right, 2x's, and then times 3x's. And then I'm going to re-simplify this and get x to the fifth. Okay, there's the first one. Now let's try the second one. We're still looking for this pattern. I've got 9 a's, so that's a lot of a's. I'm going to write kind of small here. Okay, there's my 9. Let me count 1, 2, 3, 4, 5, 6, 7, 8, 9. And then I've got one more. So I'm going to tack on 1. And that means I'm going to have a total of 10 a's. So I can simplify that to a to the 10th. Okay, let's try another one. Okay, this is w to the 7th times w to the 3rd. So 1, 2, 3, 4, 5, 6, 7, 1, 2, 3. I'm going to write to the comic over here. And then I'm going to count up how many W's I have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I bet some of you are already seeing what the pattern is. Okay, and that's awesome if you are. That's really good. Okay, I'm going to do the next 3, and then we're going to talk about formalizing this pattern a little bit going forward. Okay, the next one. I have more than just letters here. I've got numbers. I'm still going to expand this, though, so I can see. So I've got 2, and I've got 2 x's. I've got this -3 here that's just kind of hanging out, and then I've got 4 x's. So I'm first going to do 2 times -3 to give me -6, and then I've got 1, 2, 3, 4, 5, 6 x's. So I can simplify this to -6x squared. The next one, I've got 3 and 9 a's. Okay, I'm kind of losing space here. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And then times 5 times a. Okay, we're just going to do that one over here. Okay, so I've got 3 times 5. I know they're really far apart, but we always put our coefficients first. So 3 times 5 is 15. And then I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 a's. See how long this is taking? I have to like write them all out and then count them all up, and this is taking me a long time. Like, there has to be a much easier way, okay? The last one, -w to the 7, the negative's just hanging out. The negative is not attached to the w, it's attached to the w to the 7th. So we're going to leave the negative out, write down 7 w's, 5, 6, 7, and then w to the 3 more, which is going to give me -w to the 10th. So here is the pattern you should be seeing as we're going along here. In number 1, I got an exponent of 5. How is 2 and 3 related to 5? Well, 2 plus 3 equals 5. Let's see if that pattern holds. I have a 10 here, and this is an exponent of 9 and an exponent of 1. 9 plus 1 equals 10. Huh. Here, I've got an exponent of 10. Is 7 plus 3 equal to 10? Yep, and all I'm doing is adding those exponents together, right? Here, I've got a 2 and a 4. 2 plus 4 equals 6, which is what I have here. This I'm going to write in the 1, and this is a habit to get into, is to always write in your invisible ones. It's really going to help you. 9 plus 1 equals 10, which is what we had here. And then the last one, 7 plus 3, also equals 10, and that's how many w's we had down here. So this is a pattern that we see with exponents, is that when you're multiplying terms like this, all you have to do is keep the base and add the exponent. So the pattern that I see, scroll back down here. What is my laptop doing here? All right. The base stays the same, right? Notice that the base didn't change. I had a here, a's there. The base stays the same. And you add the exponents. Additionally, I'm also noticing that I do have to multiply those coefficients. Right? For these problems, I got 2 and -3, which gave me -6, 3 and 5, 15, and I had a -1 right here. Okay, so that's like a little extra additional thing that when we multiply these terms, we have to multiply the coefficients. Okay, so I'm going to put this in a formal law. We call these things laws of exponents. It's a rule that a law is something that will always work all the time. We call it a law in math. So we call this the product rule. Product means multiply, and there's a formula for this. Now, reading this formula is kind of weird. You have to imagine that A and B are numbers. And this is saying, look, x to some number times x to another number means you're going to keep x, but you're going to add those two numbers together. Okay, that's how we read this formula. You have to kind of pretend that A and B could be anything. Okay, so what does this mean that I do? Well, it means that you multiply the coefficients and then you add the exponents with terms of the same base. Okay, and the proof here is that if I expand these, and we've kind of already done a few before, if I expand these, how many 2's do I have? I have 2 to the 5th, and 2 plus 3 gives me 5. Okay, now this is not exactly a proof. I'm not going to show you a proof because it's really complicated, but this is a basic idea of why this works. Okay, so how can we do this easier? How can I do this without expanding this? Like, I don't want to do this. I don't want to do blah, 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 blah. That's terrible. I don't want to do that. It takes too long. So I'm going to use my law. I'm going to do 5 times 6, which is 30, and then I'm going to do 8 plus 2 to give me 10. And boom, that's all I have to do. I don't have to expand it. I just know to add the exponents. Okay? This is much, much less time consuming. Okay? So I'm going to do the next one. 3 times 6 is 18. I keep the n as a base. 9 plus 3 is 12. Okay, now this one, I've got 2 variables. Don't panic. That's okay. Deal with these coefficients first. So 6 times 7 is 42. And when I get long problems like this, I like to cross stuff off. I really encourage it because when we get to more complicated problems, you're going to want to know what you've already done. Okay, so now focus on your other letters. Okay, I've got a u to the 5th, a u to the 9th, and then label this little 1 right here. And I've got u to the 1. Now add these all up. I've got 5 plus 9 plus 1, which is going to give me, oh my gosh, this laptop, which is going to give me 15. So now I'm going to have u to the 15th. And then cross these guys off. You're done with the u's. The last thing you have are v's. You've got v to the 9th and v to the 5th. Well, 5 plus 9 is 14, so you've got v to the 14th. Okay? So you just got to be careful and take your time and count correctly. Okay? Let's try a few more with these double variables. Letter D, I've got 4 times 9, which gives me 36. I'm going to cross off the 4 and the 9. I've already done that. I've got x to the 8th and x to the 10th. I add those together and I get x to the 18th. And then the last one I have is y to the 5th. Okay, I don't need to multiply that y by anything because it's just kind of hanging out, so I just bring it down. Okay, letter E, I put this little joke in here. I thought it was kind of funny, particularly for this problem, because I've got -6 times -4. Well, that's going to give me a positive 24. Cross these off. I'm going to label this little 1 right here to help me know how to add. I'm also going to label this one right here, because both x's have an invisible exponent. Okay, x to the 1 times x to the 1, well, 1 plus 1 gives me 2. This is a place where I see students making mistakes. They ignore the terms of exponents because they just glance at it and don't see one. But you have to write it in. All right, so be really cautious there. Y to the 4th times y to the 3rd, add those exponents to get y to the 7th. Okay. And this last one, draw in your 1's, multiply your coefficients. I've got a to the 1, and I don't have anything else, so I'm just going to write down that as a. So I've used these 3. And b to the 1 times b to the 4th gives me b to the 1 plus 4, which is 5. Okay, so this is the product rule. Going forward, you're going to be using this rule in every other learning target this unit. Things kind of build in this unit. So this is one of those things where you need to feel really good about it. It's pretty simple. I don't think the practice will take you that long, but you need to be really proficient at it. Okay, so when you come check your answers, please make sure you're getting all your correct signs, the perfect exponents. We need to feel really good about this learning target going into 8.3. All right, good luck on your practice, and let me know if you need any help.